Welcome to my course Aspects of Biochemical Engineering. In the last lecture, I tried to cover the problems on these enzymatic reactions. I tried to find out that what is the time required for the conversion of the substrate, or how much time required for a different percentage of substrate conversion. Then we try to find out that what is the effect of inhibitors on the enzymatic reaction, particularly how it is interact with the enzymes, and how substrate enzyme interaction that differs with respect to inhibitor. And then finally, I also try to discuss that how pesticide concentration, complex organic molecule like pesticide, that how it can be determined with the help of enzymatic reaction. Now, this lecture, this is a very important lecture. The reason is that I told you that one of the important aspects of this chemical or biochemical engineering, that we at the end we should try to find out for certain conversion of substrate what is the volume of the reactor. Suppose we are working with a particular industry, and industry they are targeting for certain amount of product formation, and for getting certain amount of product, that what is the volume of the reactors. Now, in one of my lectures, I try to solve similar type of problems with respect to glucose to fructose conversion by with the help of glucose isomerase enzyme. But today I want to discuss a special type of problems where substrate is sparingly soluble in water. As you know, the enzymatic reaction usually take place in the aqueous solution. So until unless your substrate is soluble, that enzyme substrate interaction doesn't take place. So the solubility, that means solubility is a very important factor. Solubility of the substrate is very important factor, and also that cost of the substrate, that also very important factor, because suppose if the cost of the substrate is very high, so we always expect our conversion of the substrate should be as high as possible. Now, let us go to the problem. Now, the D minus hydroxy phenyl glycine, this is the complex molecules, is a optically active intermediates in the synthesis of broad spectrum antibiotics amoxicillin. We use I think day to day life lot of antibiotics doctor recommends for the curing different type of disease. One antibiotic is largely used, that is the amoxicillin, and this intermediate is among other produced from Hydantoin derivative by means of enzyme Hydantoinase. So Hydantoin derivatives, that is the name of the compounds substrate. The Hydantoin derivative is poorly soluble in water, about 1 kg per cubic meter. So their Hydantoin derivatives is very poorly soluble in water, and so the price of the substrate is cost determining, and the degree of conversion should therefore be as high as at least 99%. The cost of the substrate is very high, so we expect the main purpose of this enzymatic reaction to get higher conversion efficiency as high as 99%. So calculate the volume needed to produce 100 kg of product per day. 100 kg of product per day by Hydantoinase in batch process, CSTR and plug flow reactor. So 3 different reactors, we have to find out that batch, and this particular problem also help you for finding out which reactor you will recommend for this particular process, because you know that when you do the calculation you find out that which reactor the size will be minimum, and your design criteria should be, one of the design criteria should be the minimum size of the reactor. Why minimum size of the reactor? Because if the size of the reactor is minimum, then the cost involvement in the process also will be minimum. Now, different kinetic constants are given, like Michaelis-Menten kinetics. Vmax is 1.5 into 10 to the power minus 4 kg per second per cubic meter biocatalyst. Km value is given. Y P by S. Y P by S means P substrate and the product by substrate. That means the stoichiometry. This indicates the stoichiometry of the process. That means 1 kg of substrate produce 1 kg of product, and degree of conversion, as we mentioned above, this is 99%, and downtime is 12 hours. The activity of the biocatalyst can be assumed to be constant with time, because if the activity of the biocatalyst is different with respect to time, then it is very difficult. Then we shall have to do the integration of that, and I shall show you in the next problem how you can solve that. So, for the batch process, so what we can do, we know the what is the batch process that we have. We have already know that TB equal to minus ds by minus Rs. Okay. So, this is exactly what we have written here, and this is integrating S0 to S. Now, this is found a Michaelis-Menten equation minus Rs equal to this equation. Then we can put these values, then we can get this equation, that TB equal to minus 1 by Vmax S0 to S, this Km by ds by S plus ds. Now, this can be converted in this form. This is xs. What is xs? Xs equal to S0 minus S by S0. This is this xss. So, if you put this value, you will find the time required for this batch process is coming about 600,753.5 seconds. Now, this is we can convert into hour. So, this is equivalent to 1.876 hours. Am I right? Now, I told you, you can remember that when we want to determine the volume of the batch process, first we shall have to find out how much product you have to produce per batch. So, I can show you again. So, what I told, in case of batch process, when you find a volume of the batch, first we shall have to find out amount of product to be produced per batch. So, but when you in this problem we target maybe 10 kg of product. The basis, what is the basis? 10 kg of product per day. Let us assume that. Okay. Now, when you try to find out the batch volume, so we shall have to find out, to get this much of product, how many batch you have to operate per day. Because if you know the number of batches to be operated per day, from that we can find out how much product is to be produced per day. Now, if you know how much product is produced per day, then from the stoichiometry you can find out amount of substrate that required per batch. Am I right? Now, once you know amount of substrate required per batch, then if you divide by initial substrate concentration, then what you will get? You will get the volume of the reactor. Very simple. Very simple. You can find out the volume of the reactor. Am I right? So, let us see how we can solve this problem. Now, here Here the total time is coming about 13.876 hours. This is the batch time plus downtime. I told you in case of batch process there is a downtime you have to consider. What is downtime? Downtime include the time required to take out the material after the reaction is over, and then you clean the vessel and also refill the vessel, because this downtime is very much we consider as the idle time, because during that time no reaction takes place. So this, when you try to find out the volume of the reactor, then we shall have to find out that we shall have to add this downtime with the batch time. So total time that required in the batch process is coming about 13.876 hours. The number of batch per day is about 1.773. Am I right? Now, how much product we shall have to produce? 100 kg. So if you divide by 1.73, so how much product you have to produce per batch? 57.8 kg of product per day batch. Am I right? Now we already find out from the stoichiometry 1 kg of substrate can give 1 kg of product. Now if it is like this, we can easily say that for the getting this much of product, that we require same amount of substrate, that is 57.8 kg of substrate. But in this problem, that conversion efficiency has been given 99%. Am I right? So this is to be divided by 0.99. So actual amount of substrate required, that will be 58.4 kg. Now I told you the volume of the reactor, then what will be equal? Now initial substrate concentration, in this problem the initial substrate concentration is not given, but certain criteria is given, that since your substrate is very costly, and then they're saying that this is the substrate is the limiting factor. So what we assume, the maximum possible substrate concentration to get the maximum amount of product. Thus, and what will be the maximum amount of substrate concentration? That will be the solubility of the substrate. Whatever solubility we have, and solubility of the substrate in the water is about 1 kg per cubic meter. So if it is like this, so I can assume the initial substrate concentration is 1 kg per cubic meter. So this, if you divide by this, you will get the volume of the batch process. This is how you can easily find out volume of the batch process. Now let us see how we can find out the volume of CSTR. Now in case of volume of CSTR, the tau CSTR is nothing but the space time of continuous start tank reactor. S0 is the initial substrate concentration minus S minus RS. So this is like this. Here is the S0 and this is the S. Here is, so here at the under steady state condition, here also S. Am I right? And then we can write this equation is in this form, and finally we can get this this particular expression, and then we put the value of XA that 90 XS is 99% conversion, and then we find out the tau CSTR, this is equal to tau CSTR value is this, and once you know tau CSTR value, then we can convert in terms of hour. Am I right? Now in this problem, one thing we know, tau CSTR is equal to what? Equal to V by F. Am I right? What is F? F is the volumetric flow rate. Now here we shall have to find out the volumetric flow rate. How you can find out? How much substrate you are using per day? 100, because 100 kg of product per day. Now for 100 kg of product, how much substrate is required? 100 kg per day. Same amount of substrate, because this is 1 kg of product produced from 1 kg of substrate. The actual amount of substrate required per day will be what? 100 divided by 0.99, that is 101.01 kg per day. Am I right? Now, actual amount of substrate required, this is in day, we can convert with respect to hour if you divide by 24, then because 1 day equal to 24 hours. So, it is coming about for 4.21 kg per hour. Now, this substrate concentration, when we divide by the initial substrate concentration of substrate, now this unit is kg per hour, am I right? And this is kg per hour, and this is kg. This initial concentration is kg per unit per cubic meter, am I right? So, so kg will cancel. So, this will be becoming cubic meter per hour. That this is coming out 4.21 cubic meter per hour. Then now the tau CSTR already we find out 2.75, and if you multiply it by, so V will be equal to tau CSTR into F. So, if you like this, we multiply, we find out the volume of CSTR. This is 11.57 cubic meter. Now, let us see in case of plug flow reactor. Plug flow reactor, we can similarly find out the same that this tau plug flow reactor will be same as T batch, because we know that their expression is same. So, both tau plug flow reactor, what is the expression we have? Minus ds by minus rs, am I right? This is equal to T batch. So, since it is like this, so for the same 99% conversion, we have the value is same, the time requirement will be the same. Now, from this we already find out the flow rate. In the previous problem we already find out the flow rate, and tau plug flow reactor is the volume by flow rate. So, if the volume of plug flow reactor is we can easily calculate like this, 7.889. So, in this problem we try to find out the batch process volume is 59.3 cubic meter, and CSTR 11.57, and plug flow reactor 7.89. That means our recommendation is the plug flow reactor. So, plug flow reactor will be most suitable for this particular production process. Now, let me go to the other problem, because the other very interesting problem that we have, that is regarding we know that enzyme has lot of application in the detergent industry, particularly for the removal of stain that we have in the cloth, that can be removed with the help of the enzymes. I can give the example that if we have the blood stain that we have in the cloth, then if we use some protease enzyme that can remove the blood stain. Now, this problem is something different, because this problem we will be dealing with lipase, because due to presence of some kind of lipid or fat, or sometimes your cloth also will be giving some kind of stain. So, let us see how we can solve this problem. The lipase is being investigated as the additive for laundry detergent for the removal of stains from the fabrics. So, the general reaction is that the fats, when in presence of lipase, it produces fatty acid and glycerol. So, this is the ester. I know that you all know that fats is nothing but esters of alcohol and the fatty acid. The Michaelis-Menten constant for the pancreatic lipase is 5 millimolar. At 60 degrees centigrade, lipase is subjected to deactivation. I told you that deactivation is a very important characteristics of the enzyme, that the half life of 8 minutes. I already discussed what is half life. Half life means time required for reducing the half of the activity of the enzymes. The fat hydrolysis is carried out in well mixed batch reactor, which simulate a top loading washing machine. The initial fat concentration is 45 grams per cubic meter. At the beginning, of the reaction, the rate of hydrolysis is 0.07 millimoles per liter per second. How long does it take for the enzyme to hydrolyze 80% of the fat presence? So this we shall have to, that means when you talk about the removal of stain, that means how long we should soak the cloth in that particular detergent so that your stain can be removed. Now different these values, so because I told you before also, when you try to solve any kind of problem, I request all of you, please write down what is the data is given. The Km value is given here, so this can be, we can convert it in the Km mole per cubic meter, that we can convert in this unit, and then and this conversion, I hope you understand that 5 into 10 to the power minus 3 gram mole per liter. Am I right? So how you convert, I told you, if you want to convert in the cubic meter, so you write 1 cubic meter. Am I right? 1 cubic meter is how much? 1 cubic meter equal to the per cubic meter. So so you have to find out this. This is 1000 liters. Am I right? So so anyhow, that so the concentration is coming about 5 into 10 to the power minus 6 gram moles per cubic meter, and H0 is 45 gram mole per cubic meter, and and so 80% substrate is converted, so 20% is remaining. So 0.2 into 4.5, it is coming about 9 gram mole per cubic meter. Now the rate of deactivation, that because this is like this, that deactivation, when you discuss, that is the activity of the enzyme, that is decreases like this. Am I right? Or so E, that is enzyme activity with respect to time. This slope, this is equal to, this is RD actually, because this is equal to KD into EA, the enzyme concentration. This is how we have find out. This is RD equal to this one, and so enzyme deactivation will take place like this. This is DA, and if we integrate this, you will get this kind of equation, and this is DLN EA, this ln EA equal to KD into DT. Am I right? Now if you integrate 0 to T, and this is E0 to EA0 to EA, then what we will get? EA equal to, you can, this is ln EA by S, the EA equal to will come EA0 into e to the power KD into T. This minus sign will come here. Okay, so we can easily find out that. Now another thing is very important, that is Vmax is related with Kcat like this, Kcat into EA. that now EA is already we determined this is equal to EA0 into e to the power k dt k1 dt. Then this is equal to Vmax equal to Vmax 0 e to the power k dt. So we consider 0 stands for the initial substrate concentration. Now the rate of change of the substrate concentration can be given like this. Then this we can represent it in the form of this, because the initial substrate concentration we can write like this. Now if we integrate that value, integrate that particular value, that minus ds is the Vmax e to the power minus kd into dt, and this equation is coming like this. And we know that this is the kind of integration differentiation that we have, d by dx e to the power ax equal to ax. This will be a into dx. This is equal to ax plus k. If we use the same thing apply here, this equation we can solve in this form. And then with this is the boundary condition we have at t equal to 0, s equal to 0. Then we can put this equation like the s0 equal to this, and therefore k will be equal to k. I can take this side, and this equal to like this. Now putting this value in this equation, in the k equation here, then we can get this final equation is there. So this equation we can modify in this form. Now in this given problem, the Vmax 0 value is given, and T half value is given. So and Kd value we shall have to find out, and so that we can find out the how much substrate is converted the So T half equal to T2 into this we know that T2 into Kd. The Kd will be equal to what? This value. And then if we previous equation, if we put all these values, we can find out time required for this particular reaction, that we 80% the fat degradation. So our answer to this problem is that is required 942 seconds time, that for the hydrolysis of 80% of fat. Now another problem, similar problem we have, that penicillinase inactivates the penicillin, and one form the molecular weight is 30,000 gram per mole, has the initial active site, and kk value is given, km value is given. In response to the treatment of 5 millimolars penicillin, 1 milliliter suspension of the bacteria release about 0.04 microgram of enzyme. How long will it take the half of the initial amount of penicillin to be inactivated? And that means you have to find out that what is the time required to remove half of the penicillin, to degrade the half of the penicillin. That is we shall have to find out. And initial penicillin concentration was 5 millimolars. Then what is the concentration of penicillin to cause the enzyme to react half maximum velocity? Then second suspension of bacteria release 0.06 micromoles per milliliter of enzyme. Will this affect? The answer AB, and if so, how? Now initially that it was the 0.04 microgram. Now it is 0.06 microgram. If it is released like this, that is going to happen. This is also per milliliter, because 1 milliliter of cell suspension is there. And modified the penicillin acts as a competitive inhibitor if the affinity of enzyme for penicillin and modified penicillin is the same. What concentration of inhibitor reduce the rate of loss of penicillin 5-fold low of penicillin? So this is the problem that we have. Now we shall have to let us see how we can solve it. I hope this solution is given. I hope you can easily understand how it is solved. And initial problem is what is the time required to degrade the half of the penicillin. The initial penicillin concentration is this micromoles. So so this is S by 2 is this, and velocity of reaction is this. So kcat value is given there. E0 value, from the kcat value we can find out the E0 value, because Vmax equal to kcat into E0. So we can find out, from that we can find out Vmax value. Once we have this, we can easily find out that the V value is this. From the equation 1 we can find out this V equal to 0.98 into Vmax. We put this Vmax value here and we find a V value. Once you have the V value, we have the half the degradation, how much time is the velocity is equal to, this is equal to we can find out this. This is t minus t2. So this is not there. So t2 we can calculate. This is divided by v. So then t2 will be equal to say 16.025 minutes. Now next problem, that next solution that we have at v equal to Vmax by 2 is equal to km. Therefore that we can easily find out, because Vmax value already we know. So we can easily find out that S value we find out. So we can find out what is the S value. The km value, from the km value we can find out the S value. And part A deals with the time required for inactive half of the initial amount of penicillin. As seen in the solution 1, this time is depend upon the initial concentration of enzyme E0. By solving T2 E0 equal to this, we get T2 is this, and thus the time required for inactive half of the amount is decreased by 1.5%. So that question was that if you increase the enzyme concentration, how we are going to affect this system. And then part other than is substrate is the velocity at which vehicle, since this parameter is independent of the initial substrate concentration, initial concentration is 0, there is no change in the substrate concentration. So so this is the typical problem that we have. And this is then finally we can find out the inhibitor concentration. I am not going in details. So I hope from this equation, same as we have done before, it is similarly solved it. So I hope you can understand that this is 5 times this velocity. If you increase that, what will be that 5 times. So from that you can find out that. So so the final conclusion is that an inhibitor concentration 2 into 10 to the power minus will reduce the rate of loss of penicillin by 5 folds at low penicillin. So that is kind of conclusion that we have from this particular problems. So in conclusion, what I want to tell, that in this particular lecture I try to discuss that how you can find out the volume of a different type of reactor, batch, CSTR and Plug-4, particularly in case of sparingly soluble substrate. And also I try to discuss other different aspects, that how that life is, that which is very much used in the detergent industry, how it is activated, because how much time is required for removal of the fat, that how we can calculate. And finally we are talking about the penicillin, deactivation of penicillin with the help of penicillinase enzyme, how it affects that activity of the penicillin. So I think it will be better if you practice this problem, because this required lot of practice and if you have any kind of problem, I will be very happy to answer it. Thank you.